So, welcome this morning. Um, Last time we talked about Fourier um, synthesis and um, how we can describe any function as a sum of sines and cosines. One element was that we can divide a function into its even and odd part, and the even part corresponds to the cosines, and the odd part corresponds to the sines that we add up on top of each other. This is essentially what we call Fourier analysis. Any function can be under some conditions that we're not too much concerned with here. In this lecture, we leave that to the mathematicians, but for any reasonable function that we deal with in graphics, we can take this function and represent it through Fourier synthesis as a sum of sine and cosine functions with different amplitudes. Just add them up. For a general function, that's a continuous integral over sines and cosines of various frequencies, of continuous frequencies. And at the end, we also looked at periodic functions, in which case it turns out that we actually get away with not an integral over a continuous set of frequencies, but actually a finite sum, an infinite sum, but a sum instead of an integral over frequencies, because if the signal is periodic, then the sines and cosine have to fit into that segment of the function over which it is periodic, the wavelength, so to say. And that excludes essentially every frequency that is not a multiple of or a fraction of the wavelength, a multiple of the frequencies. And so we kind of stopped by looking, where did I want to start? I want to start quickly here. We, at the end, looked at some, let me rearrange my windows here. We looked at typical relevant functions like the sine function here offset by 1/2, and its Fourier transform, which essentially is this single frequency here because it's off, which is 1/4, because the wavelength is 4, as you can easily see. Oops, and I'm pointing at the wrong window again. The frequency is 1/4, because the wavelength here is obviously 4. And we also have what is often called a DC component, a constant contribution, which is essentially the average value because that sine wave is offset. The square wave we've looked at, this is just a sum of all the odd multiples of sines, 1, 3, 5, 7, with the amplitude decreasing as 1/3, 5, 7, and so on. You could kind of nicely see this over here with the discrete wavelength that show up here. And then for a scan line of an image, we see that this is a typical representation of such images. It has a strong, it has obviously a strong component in the average value because all values are positive. So we definitely have a DC value, right? Images, we don't have negative values. There's no negative light. And then typically the frequencies fall off fairly quickly towards higher frequencies. So we have stronger low frequency contributions, and then they fall off towards higher frequencies. And we'll today, when we look at anti-aliasing, that will become a key part. But again, when we look at supersampling. So in 2D, if you do a 2D transformation, this is essentially the same thing. You do a 1D transformation for each scan line, and then you do another 2D, then you do another transformation in the y direction. And you end up with these Fourier diagrams where the DC component is now in the center, so that's the average of the image. and you kind of get the streaks here, which each of the streaks showing contributions of edges in the image here. And as you know, edges have infinite contribution. So you the edge is the direction of the, so these lines here are the directions of edges that are orthogonal to this line. So it's probably this one here corresponds to this really strong edge here. And again, we have the low frequencies near the center, and then we go to higher and higher frequencies as we go away from the center. So it's a almost one-to-one correspondence between the 1D and the 2D, except there is this orientation aspect. So we stopped before we started to talk about convolution. This is an absolutely crucial part. I should actually color the title of the slide red. We will use this for many of the other things that come up. It's crucial to understand aliasing and anti-aliasing. It's in the very simple thing here is that we can define the convolution of two functions f and again, I should point over here. We can have the convolution, which we indicate with this cross in the circle here, the function f convoluted with the function g. And then this, of course, is again a function that we can evaluate at some value x here. And this is the convolution operator is defined as taking the integral of f over tau times g shifted by the value x. So essentially, you take this function g and you shift it across the from minus infinity to plus infinity, and then you multiply these two functions, right? For each value of x, you multiply this and integrand over from minus infinity to infinity. So if you look at here on the images on the right, essentially you're taking these two rectangle functions and you shift the one rectangle from minus infinity to plus infinity. Of course, this is usually 0, right? Because the rectangles, the function outside of the rectangle here is 0, and so obviously the product is 0. It's only non-zero if these rectangles start overlapping. They have the same width, so at the top where they fully overlap, you have this maximum value, which is so width 2 and height 2. So this is obviously 4, and so that when they start overlapping, this linearly increases. Actually, this is much better explained here on the next slide. Here you kind of can see this is a slightly different rectangle, but right, you kind of shift the one rectangle with respect to the other one, and then you record the product, the integral over the product of those two functions as the result, which is plotted below. And so it's all 0 except for when the position of the green rectangle, which is kind of with respect to its center, right, when this starts overlapping, then we get this linear increase and until it fully overlaps, and then we get this decrease. And you can do this for any function. So here on the right-hand side, we shift this rectangle over this whatever function it is, and you see that, right, essentially we get as we shift this, we get the integral over this red area here. Essentially, we take a section out of this other function, integrate over that. In this case, the rectangle has height 1, so we just essentially cut out that respective part of the other function. And actually, this is something we will do as well when we do reconstruction filtering a little bit later today. So let's just go back. Did I miss anything? No, this is pretty much the convolution. So you take one function, you shift it over the other, and you record the integral over the product from minus infinity to infinity. Yeah, so that was just the definition of the convolution. So now we have the convolution theorem. And we introduced the Fourier transform, and there's a nice relationship of doing a convolution in one of the spaces. So let's say in the spatial domain, in the image domain, right, or in the normal way we define our functions. If we do a convolution there, that it actually turns out that if you look at what is the result in the Fourier domain, in the frequency domain, then if you do a convolution in this one space, you do a multiplication in the other space, in the frequency space. And the same is true in reverse. If you want to do a convolution in frequency in Fourier space, right, that corresponds to a multiplication in the normal or spatial domain. So spatial domain, I call the spatial domain because we're integrating over an image in the X and Y direction. Here we only do it one dimensional, but as I just showed you, doing it in 2 dimensions is just more or less the same thing. And another way to think about this is, and this explains something I've introduced last time. So if we have here a box function, so width 1, height 1, centered at 0, and we take the product of the 2 functions, then the convolution of the 2 box functions here. And we just saw that what that is. So the convolution of 2 box functions is obviously the 10 function. So here's just this other notations. So these are the rectangle function, the convolution between the 2. The Fourier transform, you remember this empty dot with a solid dot. So if we do the rectangle, the Fourier transform of that was the sinc function, which is depicted down here. Obviously, the same is true for the other rectangle. And so the Fourier transform, if we do that in the normal, if we do a convolution between these 2 rectangles, right, that corresponds to a product in the Fourier domain. So the product between the same 2 sinc functions is obviously sinc squared, right? So, and you remember that I told you last time on Monday that the Fourier transform of the 10 function is sinc squared. And now you see clearly why that is the case if we take the convolution theorem. I will not go and will not prove this here, but can be fairly easily shown that this is true. Yeah, so that's really important. Convolution in one space corresponds to a product in the other space, and vice versa. We'll use this at some key places going forward. So convolution is closely related to filtering. So typical image filtering, so you might have seen this before. So it can take an average of an image over some neighborhood, which essentially corresponds to, you have your image here at the bottom, you define a filter, let's say a 3x3 filter here, with some weights. Essentially, we interpret the values of this filter here, which is essentially a small image with each pixel containing a weight. And then if a filtering operation would that correspond to take this filter, apply it at a certain location, sum up the pixel values of the underlying image times the weight from the filter, and sum this up over all the affected pixels, right? And the result of that goes into the filtered image, the resulting image. And that, yeah, so, and you can directly see that this is a convolution, right? You have one function, which is the image itself. You have a second function, which is the filter. And then you shift this filter over the other function. You do the product of the 2, and then you integrate over all of them, which essentially means since the filter typically has finite support, so it's 0 outside of of this filter image here, right? So you think of that as an infinite function that's 0 everywhere except for where these 3x3 pixels here in this case are active. And so the integral simply corresponds to multiplying these and adding this up, multiplying the pixel values with the weights, adding this all up, and then that's the result, and I store this back into my resulting image. Now, as you saw, of course, a convolution in one space corresponds to a product in the other space. So, for instance, you can, if you do Fourier transform of a function into a frequency space, then a product is much easier. Yeah, so you can take the image, you can take its Fourier transform, you can take your filter, do the Fourier transform of that, and then in the frequency space, you can simply do a product, which is a pointwise function, right? The nice or the bad thing about the convolution is you have to take this integral from -infinity to infinity. So it would be nice if the product would be much nicer. The problem is that, right, this finite box filter that we sometimes want to use, the Fourier transform of that, as we just saw again, is an infinitely supported sinc function. So it goes out to infinity. And so you have your product, you have to integrate over an infinite support. So that's not very nice. So that causes lots of computations, and you have to approximate this. Also, the sinc function has negative weights, which obviously doesn't make a lot of sense, right? It could happen if where your sinc function has negative weights, you have a strong pixel value. So you sum up lots of negatives, and you end up with storing a negative value, or trying to store a negative value, which obviously doesn't make any sense for an image because, as I mentioned before, we don't have negative light, and so that doesn't even make sense. So there's some problems with using convolution in the Fourier space, and that we have to take care of. Yes, and so filtering in what I essentially just said, if let's say you have a function here and we want to do a so-called low pass filter, this is essentially a filter which throws away all the high frequencies, and that corresponds to a multiplication with a box function, right? So we have the original function here at the very top, and we multiplied with a box function, which essentially nulls out all the high frequencies that are further away from the origin here. The box function is 1 here within the box. So we essentially only get the part of the function that is within the frequency range that's covered by this box. Now, if we wanted to do that operation in the Fourier space, which we could do, right, but then we would have, here we were doing a product, and we would have to do a convolution with a sinc filter in the Fourier space. There's also a high pass filter, which is essentially the inverse of the low pass filter. So essentially you use 1 minus the box function. So essentially you cut out all the low frequencies and only leave the high frequencies. That essentially corresponds to an edge filter, right? Because we saw when I introduced the Fourier transform, you saw that for the Fourier transform for the box function, which is essentially 2 edges, right? We had to add infinitely many frequencies, infinitely high frequencies, and so that's essentially what you see whenever you get to infinite frequencies. This corresponds essentially to an edge. And then there is a bandpass filter where you essentially take the differences of those 2 box functions. You cut off some high frequency, maybe you cut off some low frequency, so you only have an intermediate band of frequencies that you might be interested in. It's not typically that interesting for us in graphics. And so here is a high pass filter, a low pass filter. We have the original image here on the left. We throw away all the high frequencies, which essentially means we are blurring the edges, right? The edges are not as sharp anymore because all of the high frequencies that make them as sharp, you remember, right? As we added more frequencies to the box function, more or higher frequencies to the box function, right? The edge became sharper and sharper, and essentially we're throwing some of those away now, and this leaves us with blurred edges. If we do the opposite, you do a high pass filter, so you remove the low frequencies, then essentially what you're getting is only the edges in the image. And that's actually what, if you look at image processing, that's what the edge filters are doing. Okay, so that's the remaining slides from last time. Oh, I see there's a question, is convolution commutative? Let me think. Yes, it should be. I mean, you can easily do the math. So it's you do an integral over a product. I think it should be. I would have to do the math, but it feels like it should be. If someone knows, knows for sure, please provide an answer here. I would have to check. Okay, so with this, switch to our slides from today. Let me move this over here and show you the slides. So now things become more interesting. So we'll look at sampling theory. And we need all of the machinery we've just created for doing this. And one of the key elements that we need for sampling is we want to use the Fourier tool that we just looked at. And but one thing we need is to take a sample. And a sample, taking a sample of some function, is essentially multiplying this function with the delta function. Now you know what the delta function is. It's essentially, right, a function that's zero everywhere except at zero. And there it has an infinite value, but scaled in quotes, such that if you take the integral over this delta function, any integral over the delta function that contains the singularity at zero, then the result of the integral is 1. Okay, so it's very special. It's not really a function, it's a distribute. Okay, thank you very much for just confirming that it is commutative, the convolution operator. So this is taking a sample, right? Is looking at a function at a single point x, and so taking the function, multiplying this is with the delta function that it has been shifted to some location x, is exactly what taking a sample is. And for using the Fourier machinery that we just introduced, we have to look at what is the Fourier transform of a delta function, and it ends right. We saw that as you make things tighter together or smaller, then the Fourier transform gets wider, right? If we had higher frequency sine wave, then the Fourier transform was a sine wave, but it had increasingly longer wavelength. So there is this inverse relationship there. And so if you have an infinitely thin box function, which essentially is what the delta function is, you squeeze the box to 0 width, while at the same time scaling it in the y direction with the same scale, inverse scale factor, so to say, then you end up with a box that is infinitely wide. And so the Fourier transform of the delta function happens to be the constant function, and vice versa. And again, I'm pointing at the wrong slide here, the wrong screen. So, but we don't want to just take a single sample. We actually want to take a regular sampling, right? So we're taking pixels. So they have equal spacing in the x direction, and as you saw, doing the same thing in the y direction just ends up being the same thing. So we will mainly look at this in 1D and then easily generalize to 2D. So what we were interested in is what the so-called comb function, looking like a comb because it's simply an equidistant list of delta functions. from minus to plus infinity, and equal spacing of delta x between the function. The function is also sometimes called the Shah function, different names for that. And so this looks a little bit special. The Fourier transform for that still has the same properties. So as we move these samples further apart, so as we make the delta x larger in the Combs function in the spatial domain, the spacing in the Combs function in the Fourier domain here on the right, and again I have to point over here, gets tighter, or vice versa. If we move things further apart, closer together in the image side, then they get the spacing is further apart in the Fourier space, in the frequency space. Okay, again, we don't do the math here to showing that this is actually true, but we'll just use it. So there's this duality that I just indicated. Yeah, essentially, this just repeats what I was just saying. So now let's come. What does sampling actually do if we look at this if we put this all together? And so this is a kind of dense slide, but it's critical. We'll look at this in some more detail in the following slides, but this is kind of introduces the idea. We have some function in the spatial domain here, and these are symbolic representations. Okay, so this could be any function here. This is just some function. Okay, and here's a symbolic representation. On the right-hand side is a symbolic representation of its Fourier spectrum. And we just represent that spectrum, which typically falls off, as we saw from the center. We simply represent it as this triangle here, just for illustration purposes. So as we just saw, if we want to do a regular sampling of that function, we have to multiply it with the Combs function, where the distance between the Combs corresponds to our pixels, right? And if we're doing ray tracing, let's say we sample at the center of our pixels, and so we're looking at one scan line here, and the distance between the spikes of the Combs function is the distance between the centers of my pixels here. And so if I want to take a sampling of my continuous image function, right? We get a continuous wave of light into our camera. I want to sample this at equidistant spaces. Then I take the product of this function f here with the Combs function, and this gives us my sampled function. So I only have values of this continuous function now at discrete locations in the spatial domain. And so the interesting thing is what happens on the Fourier space, right? So let's say we have a dense sampling here in the spatial domain. This corresponds to a wider sampling on the Fourier domain. So Combs function, the Fourier transform, as we just saw, is again a Combs function, but with wider spacing. And so now the trick is, what does the convolution of any function with a Combs function actually give you? And it turns out that as you shift the one function over this integral, because the integral over the Combs function is 1, it essentially projects out a copy of the function f centered at each of the delta peaks, right? So for each of the peaks here of the Combs function, I get one copy of the function capital F of u, the Fourier transform of my function f here. And that's critical. That's absolutely critical to understand what sampling does. So as you sample your image, right, you are creating copies of the frequency at different frequencies. You get copies of the frequency spectrum of this function f here centered at the original location. Okay, that is what we're interested in. But you get copies at higher, many copies at higher frequencies as well. Okay, so that's fine. That's fine, right? However, if you want to reconstruct the original function, if you were to take this, sorry again, if you want to take this transform these many copies and transform them back, you're obviously not getting the original function, right? Because you added high frequencies to it. So in order to reconstruct it, we actually need to get rid of these copies, and we'll talk about this in the coming slides, right? However, so we get these copies, okay? So we here in the forgot to mention that in the symbolic representation here at the very top, we assumed that our function has a finite support, so it has some maximum frequency. This is why we use this delta function. So we assume that the high frequencies are 0 beyond some maximum frequency here, okay? And so if the spacing of our comb function in the Fourier domain is far enough apart such that these triangles don't overlap, everything is fine, okay? We do get into issues if they start to overlap, right? Because now I'm mixing the high frequency of one of the copies into my original frequencies. And there is nothing I can do to get rid of this error. This is actually aliasing. This red part here, where those frequency bands of the copies overlap with the original frequencies of my Fourier transform, I cannot undo this error, right? I don't know what is the original frequency and what is from the copies. And so as I sample, I'm doing the error if I cannot ensure that those copies do not overlap. And in order not to overlap, I need to move them far apart such that, right, the overlap doesn't happen, or and we'll see is hopefully small, because we cannot always guarantee that we don't have high frequencies. And moving them far apart means we need to sample with a dense enough sampling in the spatial domain, right? Because we make it dense here, then in the spatial domain, then in the Fourier domain, we're moving these copies further apart. It's important, really important. I'll repeat it multiple times today. Still, right? As you are sampling, you're creating those copies. If they start to overlap, you're creating aliasing artifacts, and you cannot undo them. Okay. So this was the sampling process. So I've sampled my function. Now this is my, and we have to do this, right? We have a finite computer. We cannot represent an infinite amount of frequencies. So we have to live with some finite number of samples. Okay, we've just done that. We've sampled our function with some finite number of samples. But we want to reconstruct the original function. And in order to do that, right, so here again is, here's the sampling process. And in order to reconstruct the original function, what we need to do is we need to get rid of those copies to the left and to the right, the higher frequencies. And in order to do that, the best thing we can do is a multiplication in the Fourier domain with a box function that is just wide enough, so it has value 1, and is wide enough to just copy, just cover the original frequency band, right, and up to this f max here of my triangle. Because if I multiply with this, I'm removing all the high copies, and what I get is the original one, and that I can transfer back, and I get a perfect, in theory, I get a perfect copy of my original function. So I can take my continuous function, I can sample it, represent it with a finite amount of samples, and then reconstruct it and get my original continuous function back. That is the idea, okay? Obviously, the product with the box function here, this step D here, which then gives us the result, corresponds to that I would do a convolution in image space with a sinc function, right? Again, multiplication here, in this case, in the Fourier domain, corresponds to a convolution with the sinc function. So the sinc function is, in some sense, the perfect function for reconstructing a continuous signal from a finite number of samples. Now, as we saw earlier, the sinc function is not an easy function because this has infinite support, has negative values. So a perfect reconstruction with the sinc function doesn't actually work. It could give you negative values. And so we have to do some kind of approximations, right? We cannot integrate over infinite space. So what would be the easiest thing to do? Well, why don't we just cut off the sinc function, right? You can simply say, well, I just go to from -3 to 3 here of my sinc function, and I convolute with that. So I'm just cut off the high frequencies of my sinc function. But, right, what does that mean? That means that would correspond to actually doing a product in the frequency domain and the Fourier domain with not with the box function, but with this wiggly approximation to the box function. So, but specifically, we get some higher frequencies into our result, and also we're not getting, right? We're kind of modulating some of the frequencies that we actually want to have, that we want to conserve, and they get modulated by this wiggly approximation to the box function. So that results typically in ringing. So along edges, right? If you cut off your sinc function, that corresponds. If you had a sharp edge, you sample that and you then reconstruct it, you get this ringing artifact around edges. So if you have a black and white edge, you see some dark parallel, essentially these wiggles that you see here on both sides of an edge, right? And you don't want to really see this. And here is really taking this all together and using this not with this symbolic approximation, this symbolic representation, but actually doing this with real image function. So here is my original function. We assume it is band limited. So we assume it doesn't have sharp edges. It has a maximum frequency, and you see this here in the Fourier transform, right? You have some frequencies here, but then it's all limited, and there's no higher frequencies than 1/2. Okay, so then if we sample this at the right sampling rate. In this case here, we just make sure that it's just high enough that they don't overlap. That would be sampling exactly at the Nyquist limit, right? The Nyquist limit corresponds to the frequencies that I can just represent here, twice of that. Sorry, half of that. Such that they just have the proper spacing, right? Because I have half the frequencies to the left and right, so I need twice the frequency as distance between my copies here. So I can only use half. I got confused here. I have to make sure that the spacing is twice as wide as the maximum frequencies. That means I need to sample with at least twice my highest frequencies that I have. So that moves my copies here far enough away from each other such that then if I would use a perfect box filter, I could cut out the one copy that I want, right? I only get one copy, and if I had a perfect box filter, I could now reconstruct the original signal again. So as we saw, multiplying, right, the box function multiplying with the box function corresponds to convolution with the sinc function, that we can't really do this. So maybe instead of the sinc function, we want to use the sinc squared function that would correspond to actually the convolution with the tent function, as we know. But that obviously doesn't give us the right results, because the sinc squared still gets us some of the high frequencies that we don't want, right? It's not It's not a very good filter. So we will see aliasing artifacts. We will see high frequencies of copies of these. So we will see high frequencies that show up as low frequencies. And this is shown here. This is kind of an extreme case. I'm sampling here with too low a frequency, which means here in my Fourier space, so the spacing is wider in the spatial domain, which means my spacing gets narrower in the frequency domain. My copies start overlapping, and the high frequencies of my first copies is being shifted into the lower frequencies of my original spectral band here. And so some high frequencies show up as low frequencies, and we can actually, we'll show you that in a second. So that's aliasing. Yes, and the point here is we cannot undo that. Even if we had an ideal sync reconstruction, now this doesn't work anymore. And we get artifacts. Right? It just gets worse we've already created a filter there's a sampling process that generates aliasing, and then we add a non-perfect filter to it, and which just gets more errors into our bit. And here's just again another way of visualizing this. Right? Again, symbolic. Here is my original spectrum of my function. Here's my sampling comb. I get these copies, and if the Nyquist limit is satisfied, right? If I'm sampling with the higher frequencies, higher than twice the top frequency that I have in my signal, then my spacing is too far enough apart that these copies are separated. I can cut out everything except for this one original copy and reconstruct the function perfectly. If that Nyquist limit is it's violated, so I'm sampling not with twice the highest frequencies, then those frequency bands overlap. Everything is broken at this point. I cannot reconstruct the original function. And these overlapping areas is what causes the aliasing artifact. So here's another way of looking at aliasing. So here we have a sinc function, right? And we're sampling this with a frequency that's much higher than the frequency of the sinc function, and I can do a perfect reconstruction with this. Right? Here my spatial sampling frequency is, the spatial frequency of my function is much lower than what I can represent with the sampling here. Now, sampling at exactly the Nyquist limit is not enough. You actually have to sample at more than twice the frequency. So here I'm sampling at exactly twice the frequency, and here on the top right, you see that if I'm unlucky, I just happen to sample this sine function twice in each wave period here, but just happen to sample it when it's 0, right? And so obviously the reconstruction of that function would be 0. So sampling at exactly the Nyquist limit is not enough. You have to sample at higher frequencies. Of course, if you would sample here at a slight, if you shift these samples a little bit, then you get all sorts of other reconstructions. And here is exactly what happens if you reduce the frequency, the sampling frequency even more, right? So here is our first sample. Our next one is not even at half. So we're sampling too low. And if you then reconstruct a signal with our samples, you see that we're actually reconstructing a sine function with a much lower frequencies frequency than the original, the solid, again, pointing at the wrong image here, at the wrong screen, right? This dotted line here is much lower frequency than the original function that we were sampling. And this simply is a result of sampling not often enough. And it gets extreme here in this case, where we're even sampling lower. In 2D, this is how things look like. This is a rotational symmetric function. It's kind of a sinc function here, right? The intensity drops, gets higher frequencies as I go out. And I'm sampling this with a 2D grid. So these are my pixel locations. And if I reconstruct from this sampling, obviously this sampling here is fine at the center, right? Because my frequency is much lower than the sampling frequency here. But as I go to further away from the center of my image, I'm getting all sorts of aliasing here. And other aliasing artifacts you see here, these jagged edges from insufficient sampling is an aliasing artifact, right? Remember, these sharp edges, black and white edges here, require infinite frequency. We don't have, right? We have a finite number of pixels, so we can't have infinite frequencies. And one of the results is simply that we see these staircases here. You see the Fourier transform of that. So this we just can't handle this sufficiently. Another way that's typically used for showing aliasing artifacts, or actually showing how good an anti-aliasing strategy works, is looking at such checkerboards, right? They obviously have a very high frequency. And if you put this checkerboard texture on an infinite plane and you're looking towards the horizon, the apparent frequency increases as you go further towards the horizon here. And you see that here in front, everything is fine essentially until you come here. And again, I'm pointing at the wrong screen. Until you come into those regions where now the frequencies of our sampling becomes roughly the frequency, we're approaching the Nyquist limit. And then you add specifically here in the back, you see this very low frequency, long black, white stripes, which is essentially what we would expect. And we're seeing some of the high frequencies that is in our signal, this high frequency black and white pattern, showing up as low frequencies in the result. Right? That's exactly what we're expecting. And so these are ways how we can visualize the spatial aliasing. So what causes aliasing? Just to make this really ram this home, it all comes from the sampling process, right? There's nothing else. It is as you are sampling, discretely sampling a function. If you do this multiplication with the conv function, that is where it happens, right? And if you can't do that correctly, the error is there. You cannot remove this error later on. And the problem obviously is if you have sharp edges in your image, you kind of will have aliasing, right? Because that requires infinite frequencies to represent this sharp edge. We cannot sample at infinite frequencies, so we will have aliasing. And what we will look at is, can we somehow reduce this aliasing? We will not be able to remove it completely, right? Now, in reality, in a real camera, right, we don't have this as much, right? Because we're actually not sampling with an infinitely small point sample, as this delta function represents, right? We're actually integrating our signal with respect to the support of a pixel with finite size. So we're integrating over a finite size, we're integrating our signals, the incoming light, over a finite size in the analog domain, right? So we're not taking this, right? We derived everything with this delta function here. So a camera, a real camera, actually does this integration operation. And that removes a lot of aliasing. You can still have aliasing in those cameras, of course, because there's still something going on there. It's just not exactly what we have been describing. You're not taking point samples. But in ray tracing, we are taking point sample, right? We have these infinitely thin rays that we sample with, and we'll talk about some of the solutions a little bit later. In the computer, we cannot analytically integrate, right? Because we have a finite representation, and we cannot have this analog function. We have to have a finite, a discrete representation. And so we will have to suffer some aliasing. So we will have to do some sort of numerical integration, but in order to do a numerical integration, we'll have to take samples first, right? Because we have to create this finite representation that we can then do the numerical integration with. We can still do that integration, right? But we'll get there in a second, right? It can be complex. And so it's important to distinguish two sources of error. There's the sampling error that happens as you multiply that continuous function with our comb function. That's what the sampling error is, right? That can and will introduce at least some sort of error, right? Well, it will be perfect if we don't have high frequencies, but we do have edges, perfect edges, shadows, or geometry edges. So in rendering, we cannot avoid this. So we'll have some sampling errors. But there's more errors. There's a different type of errors that can come once we have done sampling, and we have some errors already in our representation. If we then reconstruct a function, a continuous function from our finite discrete samples, we can create more errors there during the reconstruction, right? We will probably not use the perfect sinc function to do a convolution with a sinc function, because that's, as we discussed, isn't really possible. So we'll have to approximate our perfect reconstruction filter with an approximation, and that again causes errors. But those are the reconstruction errors. They're different from the sampling errors. So what can we do? Well, first of all, we've seen these spatial aliasing artifacts, staircases, moire patterns. I forgot to name the, right, when you saw the, let me just go back. So these here on the right-hand side, these are moire patterns, as they're typically called. So it's essentially interference between two frequencies, the sampling frequencies and the signal frequencies. They interfere with each other. You probably have seen or heard the experiments if you have two tones, oral tones, audio tones, and two frequencies. And if those frequencies are very close to each other, you get a result. You hear resulting frequencies of a much lower frequency. You hear a tone at a much lower frequency. That is an aliasing artifact of these two frequencies interfering with each other, and sometimes eliminating each other, and sometimes strengthening each other. And they do this at a lower frequency, which is exactly a moire pattern in the audio signal. And actually, you use this to, what's the word, stimmen, to get two musical instrument to have be at the same frequencies of their, right? You use this aliasing artifact to just remove that low tone, that artifact. That's one way of using this. Okay, so what can we do, right, to solve that? I kind of indicated we cannot completely remove it, but the best way to remove it is increase the sampling rate, right? As we increase the sampling rate, we're moving our delta function further apart in Fourier space, and the overlap is being reduced. You saw also that the intensity of higher frequencies towards, we had this fall off towards higher frequencies. And so the overlap is then, right, as we move them further apart, the overlap happens only at higher and higher frequencies, and their amplitudes are lower and lower. So we get less effect, right? Our aliasing artifact gets smaller. Some people suggest to filter the resulting signal. I'll show some examples a little bit later. That's not a good idea because, as I told you, the error has been done, right? Essentially, what you can do if you filter the resulting signal after having done the sampling, you're essentially blurring your images. And yes, you might blur the error. It might not be as visible, but you've just made your resulting signal even worse, right? You might have blurred the error as well, but you've also blurred the original function. So that is not, post-filtering is not a solution, right? So that does not make any sense. What we could do, in theory, we could do pre-filtering, right? We could take our analog signal and remove all the high frequencies, all the frequencies that are too high for our sampling rate, right? Except that we don't really know how to do that for optical signals, right? We would have to remove edges in the analog domain. Right? You can put some fat on your lens, right? That would create lots of blurring. Blurring, as we saw, is essentially a low-pass filter removing high frequencies. Yes, but then you would take a photograph of a blurred image, and that might not be what you want. We don't have a way to selectively, in the analog domain, remove artifacts or remove high frequencies as we want to do here. It's really hard to do. So we have to live with the problems that we have. There is one solution, and that's supersampling. We'll come to that a little bit later. There is a trick you can do. It's sampling high frequencies, but not having to actually store the high frequencies. There's a trick. Sampling, by the way, doesn't, so we'll get to that. Sampling doesn't just happen in the spatial domain. I was mostly talking about spatial domain. You can also look at this in the temporal domain. And you all have seen this in old movies, right? The movies are shot at 25 frame or 24 frames in many cases, particularly the old ones. And when you see a wheel of in those films, movies, then these wheels often appear to be turning backwards, which seems strange, but that again is a temporal aliasing artifact. So let's have this artificial wheel here. This turns clockwise, but if I sample this rotation to too low frequencies, so too few frames per second, right? I just happen to catch it in a position that if you take the red copies here and put them together, it appears to turn backwards, right? And that's exactly a temporal aliasing artifact that you're dealing with here. And again, to solve that, we would have to increase the frame rate, yes, but that can be costly. Post-filtering, again, doesn't work. If I would filter across the red images here, right, I would get a blurred version of this wheel here, essentially with the spokes, with copies of the spokes put on top of each other. That's not what I want, right? And again, pre-filtering is not really an option. We don't know how to do this. The only thing we can do is super sampling, again, taking many more samples in the temporal domain than we're taking normally. So pre-filtering, if we would want to do that, right, we would have the original signal here. We could do a low-pass filter in the analog domain, right? Because as soon as we go into the digital domain, we're creating the error, just want to say this once more, right? So we have to do the low pass filtering in the analog domain. Then we have a resulting function that doesn't have too high frequencies. Then I can hopefully sample it at in high enough frequencies. I get no aliasing error, and then I can do hopefully a very good reconstruction and at least remove or minimize the reconstruction error. Maybe even do it again, in theory, doing it perfectly, but again, only in theory. So where does the high frequencies come from? Right, obviously edges, geometric edges. So you see your table, and at the edge of the table you see the floor or whatever is behind your table. And if the one is white, the other is black, this creates an absolutely sharp edge there, and there's nothing we can do. Right, the one sample is black, and sample just a tiny bit away from that will have a completely different color. So that's a perfectly sharp edge. So edges, any sharp boundaries, shadow boundaries might be sharp. Textures like this checkerboard texture that we saw before. So the geometry might be perfectly smooth, but if I put a sharp checkerboard texture on top of that, then of course I've just introduced visual edges in my scene. Yeah, I cannot really avoid that. Also, yeah, illumination, I just mentioned that. I can also project light into my scene, so that might be a cause for, it's essentially like shadows, any other lighting effects here. And analytic filtering, so in the analog domain, it's almost impossible. People have tried to do this, even with the most simple filters like a box filter or a tent filter, we cannot really do this. So one of the things that people have tried in the past is if you have a rasterizer, so you want to render a triangle on your screen, you assume your pixels to be either quadratic or maybe assume them to be a circle. So often, because quadratic is not so nice and symmetric, for each pixel you actually take a circular filter over that pixel, and now you can analytically, in theory, for each of the edges of a triangle, you can actually analytically compute what is the overlap of this edge with this spherical blob here. Specifically, this blob, for instance, could be a tent function, so in 2D, so circularly symmetric. And you can also kind of, in lookup tables, depending on the distance of the edge from the center, you can analytically essentially look up what the integral is. And so you can compute this, you can store this in filter tables and in lookup tables and essentially interpolate between this. This works for edges, but it fails if you do this at the corners here, where two edges come close together. This doesn't really work anymore, or it gets so complicated that it doesn't really work, or it's not practical, let's say. So this was tried and was abandoned because it was just too costly. What is being done today is essentially oversampling. So sampling at a higher frequency that you actually represent it finally in the image. But again, this is limited because edges create infinite frequencies, and obviously that we cannot sample it at infinite frequencies. So here is the trick. Here is the super sampling idea, and it's called this resampling pipeline. And it's a little bit complicated, but once you get the idea, it's pretty obvious. So the assumption here is that we assume, and this kind of shown in this graph here, is that we have strong high amplitude, low frequencies here at near the origin, but that higher, as we get to higher and higher frequencies, the amplitude falls, right? And so the higher we go, the less energy is in these frequencies. The amplitude in the Fourier spectrum becomes smaller and smaller. Okay, that's a basic assumption. The idea here now is, right, as we move them further apart, we can remove aliasing by just moving them further apart, because the overlap is only in areas that are less have less energy. Okay, so the idea is I actually at the end I can only represent my signal as at a target frequency of f2, which is low. Okay, so that is the sampling of my the spacing of my pixel. So that's low. Okay. But what I can do is I can actually sample my original signal at a much higher frequency f1, right? So I use the higher frequency f1 to sample my my analog signal, and because that means in the Fourier spectrum I move my copies further apart, the overlap gets smaller, right, with less energy, and so the aliasing is reduced. Okay. So I made an error, an aliasing error, but that is smaller than I would have if I would have sampled at f2. So essentially, right, all of this part would not overlap, right? If I sampled with f1, I'm moving them further apart, so I'm removing the overlap. Okay, so I've made an error, but it's smaller. Now I'm in the digital domain. So, right, I've made the error, but now I'm in the digital domain. And I can reconstruct a signal based on the samples that I've taken. So I reconstruct a continuous function G1 out of the samples that I've taken with frequency f1. And we have to do this, for instance, with the convolution with a sinc function with respect to f1. Again, we might not be able to do this perfectly, but let's assume we can do this reasonably well. So we hopefully have made a small reconstruction error, and now we have an analog representation. We have an analog function G1, a continuous function G1. Now I can low pass filter that. Remember, we are already in the digital domain, right? So I can low pass this filter that function G1, and with the result of that being a filtered function G2. And I filter it, low pass filter it such that I remove all of the frequencies that are higher than f2. So I remove all of the high frequency. Again, I can do this because I'm already in the digital domain. This doesn't introduce additional error other than maybe numerical and other approximations that I might be doing. Okay, so now I have removed all the error, all the frequencies that are higher than f2. Of course, that modifies my signal, but anyway. And then I resample, and this is where the name of the pipeline comes from. I resample my function G2. And because I've removed the high frequencies, I'm not adding more aliasing, right? Because I've removed the high frequencies that would cause aliasing. And the funny thing is that the filter that reconstructs the function G1, so this reconstruction filter, and then this low pass filter G2, I can actually combine them into a single filter. So essentially I do the high the high sampling with frequency f1, and then I filter that directly the result of that high frequency sampling with the combined filters G1 and G2, and I end up with a signal that's sampled in f2 that's represented at frequency with the sampling relative to f2. But I've only gotten the original aliasing error that was caused by sampling with this higher frequencies f1, right? Still, I've modified my signal, right? I've thrown away the high frequencies, but I would have to do this anyway. There's just no way I can represent the high frequencies that are higher than f2, right? With the sampling f2 that I can afford. But I've not introduced aliasing errors. That's the I'm not sure about what F1 and F2 represent in the resampling pipeline. Can somebody tell me? Yeah, so I can try to repeat. So remember, so I have my original function, okay? And F1 is the sampling frequencies that I take. And so I could, again, this is my Fourier spectrum here. And if I sample with F1, this means I'm moving my copies so far away from each other that they that the next copy would essentially start exactly here to the right, right? And so the overlapping of this copy with the next copy is this blue region here, right? Or in other words, the next copy would reach into, sorry, I'm pointing to the wrong screen again. So this is my frequency spectrum of my function, original function that I'm sampling. I'm sampling with frequency F1 such that I get copies where the next one would be just adjacent to this one here. But you see that this copy here reaches outside of F1. So F1, because we can have infinite frequencies, so there will always be something outside. For any frequency F1, there will be something outside. Now for the next copy, that stuff that is outside here will actually reach into my block F1, the box that I've plotted here. So that will cause aliasing. But since I've sampled with F1, right, this will be much smaller than if I had sampled with F2, right, with a much lower frequency F2. But F2 is the frequency with which I can represent my image only. Let's say I only have 256 or 1K samples in the X dimension, right? But that might cause a lot of errors. So I'm sampling with 8 times the number of samples. So that would be then F1. I sample with this high frequencies, and then I down filter this with this combined filter G1 to G2 into a representation that does not create additional aliasing artifacts with respect to F2, which I would do if I had sampled with F2. Right? There would be a lot more energy here that would overlap with the next copy. So how does supersampling actually work? Sorry, there's another question I just see. So the larger spacing between the samples for F1 help us exactly, right? F2 is a higher frequency. I'm sampling with a higher frequency in the spatial domain. That means I'm moving my samples in the spatial domain. Sorry, in the Fourier domain, I'm moving my samples further, or my comb function further apart. That means my copies are further apart of the spectrum. There's less aliasing, and then I can do the filtering in the digital domain, and I'm not introducing more errors as if if I had sampled with F2, my copies would be much closer together. There would be more overlap. There would be more aliasing that I couldn't get away with. By sampling with a high frequency, I move them apart. There's less overlap. I'm introducing less aliasing, and then I can downsample that signal to the lower frequency F2 with which I represent the image. And here's how it works in image in rendering, let's say. So let's assume we do regular supersampling. Okay. For instance, we could, instead of taking a single sample per pixel, so the rectangles here are my pixels, and instead of a single sample in the center, I could just take 4 regular samples in each of the center of the 4 quadrants, essentially. Okay, so I'm taking 4 times as many samples, and then in the easiest way, I can take all of those, so compute the color from those 4 rays, and I take the average. Okay, what is the average? Well, the average is taking a box filter over those pixels, right? You just weight them with the same weight, and then you're summing them up. So you're doing a box filter in the spatial domain in this case by just taking the average of the 4 samples. So box filter in the spatial domain means I'm doing a sinc filter in the Fourier domain. But remember, that is not the filter I'm looking for. I actually want a box filter in the spatial domain. Sorry, in the box filter in the Fourier domain, because I want to sharply cut off all the high frequency stuff. Remember this on a couple of slides ago, right? So that's, first of all, taking regular samples is one way, but then the reconstruction filter, just averaging these 4 samples is not the best way. So with 4 samples, that's you typically get fairly good results already. 16 is often sufficient, but as we know, right, it will not be enough for very high frequencies, and we can have infinite frequencies, but it will remove a lot of the aliasing noise already. Yeah, box filter is the easy one, essentially corresponding, as I just said, to averaging the samples within the pixel. It turns out that you can do better, and there is essentially a kind of black art of designing filters for example, for the film industry, because at the end you're not even interested in the right pixel value. So for each pixel, at the end you take 4 samples, but you only store a single color per pixel. Okay. But this is not what you're showing. What you're showing is actually this, the pixels, you image them maybe on analog film, or you're projecting them with a projector onto a screen. There's some modification of the signal happening in the projector or on the film, or from the film to in the film projector. And so the film industry has developed this black art of designing these filters such that they also take into account the typical presentation of the films in a movie theater, and what kind of processing and what kind of modification of the signal happens there. And they try to correct for this in the filtering of their subsamples already. So there's different ways we could do this. The regular supersampling in this 2x2 grid here is one way. There's different ways of how I can do it, and right, the regular is one. As we'll just see in 2 slides from now, this is not a very good one. We could also do random samples. We just draw random numbers and take samples randomly within n samples randomly within a pixel. This is not, sounds good like a random number, right? So it's equally distributed over the pixel. It turns out that is not actually that good, because these samples could, like in this case, leave out a large part of the pixel, or they can clump together, not really giving you more information, because they're essentially taking the same value, looking at the same value. And so there's Poisson disk sampling. I don't have time to go into all the details, and I'll have a little bit more on stochastic sampling in a little bit later. So in Poisson disk, so we essentially enforce that there will be a minimum distance between samples. And there's other techniques, for instance, jittered sampling, where you start off with samples, for instance, here in the 4 quadrants of the pixels, or 3x3 subpixels, but then you randomly offset them a little bit from the center of their quadrant here. This is actually a very good technique. Sometimes you cannot randomly do this. So what hardware actually typically does today is these rotated grid patterns. They are regular, but they're rotated with respect to the pixel grid, and so you get better properties. But we don't have time to go really into these techniques in detail here in this lecture. Yes, so a typical thing that a lot, oh, sorry, there's a question. I was just wondering, if you wanted to super sampling with a ray tracer, would you cast 4 or even 16 rays per pixel? That's exactly what you would be doing. Or super sampling, a technique that only used in raster graphics. It's used everywhere, both in ray tracing, which means you have to trace more rays, which can be expensive. In rasterization, it's not as expensive because you can reuse a lot of the computation. but you can do at least some of that in ray tracing as well. We don't have time to go into all of this details, but you can find stuff. And we'll yeah, we don't go into much detail here. Yes, so there are some ideas people regularly have, and so I want to teach you that you shouldn't fall into the same trap. So a lot of what people think is, oh, I can cheat, right? So here are my pixels. Instead of tracing 4 samples per pixel, right? Why don't I trace my samples at the corners of my pixel and I share them between pixels, right? So this sample here in the middle, I can actually use this for all 4 rays. So you average for the top left pixel here, you average these dark, these 4 samples at the corner of that pixel, right? And then for the top right, you reuse the value, the shared values at the edge between the 2 pixels. That seems like a great idea, right? Because you still average 4 samples, but you're reusing them, so you don't have to trace as many pixels. Okay. Where's the problem? Well, the problem is if you look at the sampling rate, you haven't changed it. The distance between between samples is exactly the same as you had sampled in the center. You've just offset this by half a pixel in X and Y, and you added 1 sample row and 1 sample column at the edge of the pixel of your image, right? So essentially you have, right, in particular, if you think about 1K samples in the X and Y dimension at the typical resolution, or even 2K, right, that added 1 sample in the X and Y dimension, 1 more sample in the X and Y dimension, doesn't make any difference in the frequency sampling. The distance between pixel is exactly the same. And so the aliasing that you're getting is exactly the same. So what are you actually doing here? Well, you're taking the samples at the original frequency, at the same frequency as if you had sampled in the center, but after you've sampled, you are blurring because you're averaging between 4 neighboring samples. So this is post-sampling filtering. And I told you, this just makes things worse, right? So here is a post-reconstruction blur, right? So I have this hard shadow. So this is a blown up version. You have a hard edge. You get this staircase aliasing artifact. And then you put a 3x3 blur over this, right? What do you get? Well, you've not removed the aliasing artifact. The steps are still there. You've just blurred your image, right? The entire image, actually. So there is no free supersampling. Either you sample at a higher frequency and you do the work that's required, and then you get less aliasing, as we discussed with the resampling pipeline, right? As you sample, you are doing the error. And if you sample with the same frequency as in this case here, you're not avoiding the aliasing error. And blurring with more blur just blurs more. It doesn't remove the edges in the first case. So, but there is an idea that I don't necessarily have high frequency everywhere in my image, right? There might be areas where, like, I'm having a white wall that is all the same value over a huge part of your image. So why should I spend a lot of time doing supersampling there when I kind of see there are no high frequencies? So the idea is that I adapt my sampling rate to what I see in the image, right? If there is high frequencies in the image, then I take more samples. And if I don't see any differences, then I get away with less samples. Now, the problem is I don't know what the image is, right? Because that's what I'm doing in ray tracing. I'm computing the image. I don't know what's in the image unless I have taken the rays. And so some of these adaptive techniques, they have to guess how much, what is the frequency in the image space. And just to finish this, is the idea is you start with a coarse sampling. So here's one recursive approach to adaptive supersampling. Is you start with sampling at the pixel borders. So that is, as we just discussed, essentially the same frequency. It is exactly the same frequency as if you had sampled in the pixel centers. Additionally, so you start with A, B, C, D. And additionally, you take one more sample in the center called E here. And now you compare for each quadrant, you compare whether there is too much difference. So you compare A and E to figure out if you think there is stuff going on there. And so essentially, if A and E are too different, then you would subdivide the top left quadrant. In this case, we don't do this. And you look at E and B in the top right, and then in this case, we figured out that, well, there is too much difference, let's say, between E and B. And then you essentially recursively take any additional samples. So that would be F, G, and H. And you again recursively look at if there's too much differences in each of the quadrant. In this case, you figure out that, right, between E and G, there's too much, and you subdivide. Sorry, I was wrong. So for the quadrant here, yeah, no, it's correct. And then you take J and L as well, and so on. So you simply recursively subdivide, and then for the top left corner, for the top left quadrant here, A and E, since we didn't subdivide, we take the average of A and E. So there's some filtering happening here. And then for the recursive part, you do the same thing. And you can easily recursively do this filtering operation by just looking at the size of the quadrants. And you can look at the equation here. Now, instead of just looking at the differences between pixel values or the colors, actually the RGB colors, the typical thing that people do is, first of all, they convert to black and white, to gray values, because we're mostly sensitive to that. And they are not only looking at the absolute differences, but at the contrast, right? So the relative difference between pixel values. Also, instead of going to black and white, you can do a color contrast or color differences. We don't typically want to do this in RGB. We'll come back to that, how to do differences in color or to compute differences in color when we talk about color spaces a little bit later. So with this, I'm stopping here. There's a couple of slides left about stochastic supersampling that we'll then finish on next Monday. It's just a couple of slides. So officially the lecture's over, but if there's any images, I'm happy to stay a little longer and answer any questions you might have. Just wanted to finish this. Are there any questions?
Yeah, hello.
Yep.
This adaptive supersampling seems to introduce a lot of overhead as well.
Well, I mean, that's a little bit longer answer. There's different forms of overhead. Yes, of course, you're adding more samples but only where you see in quotes that it is necessary. So you could argue that's not really an overhead. It just adapts to the frequencies you see in the image, or the structure you see in the image. There is overhead often in terms of how to implement it. If you have a sequential ray tracer that traces one ray after another, the overhead is minimal. But if you ray trace in hardware, right, you have to trace the corner rays first, and then you have to go back and compute the other rays, and that might require a lot of overhead if you optimize for hardware. So it's a little bit more difficult question to answer.
Okay, thank you.
Any other questions? that doesn't seem to be the case, and I guess you need to go to your next lectures as well. So thank you very much, and we'll see you again, or we'll see each other. Well, I guess you see me, I don't see you anyway, but we'll be together again on next Monday. See you then. And yeah, stochastic supersampling, we'll finish that, and that's a really interesting part as well. And then we'll move over to also then get to the human visual system and color perception and color representation soon. Okay, thank you very much, and see you on Monday.